All right, well, welcome everyone. I am JJ. Let's go ahead and tackle an example problem. So in this one, we're saying we have an object shown here. It's supported by a pin at A and a rocker at B, and that rocker is on an inclined plane. Let's find our support reactions. What's going on at A and B? We know if we're doing support reactions, we're making equilibrium equations. Anytime we have an equilibrium equation, we should have a free body diagram that ties in and illustrates what we're doing. So let's start out here and make a free body diagram. So I'm going to circle around my object. I'm going to try to cut through my supports so I completely free this from whatever's holding it up. I'll circle around as I do that. Anything that my circle passes through should show up as an unknown in my free body diagram. So if I start up here, I could slice down and cut that pin at A, and then just keep going. I cut through my rocker at B, and I could go up and around the rest of my diagram. We'll get my entire thing circled in here. I've cut a pin at A, I need to have AX and AY. I've cut my rocker at B, I'll need to have a force down there, just perpendicular to the plane it's rocking on. Again, as we get more and more familiar with free body diagrams, we'll probably skip that step. But if you are struggling with free body diagrams, circle around everything. Circle it, cut through your supports. It'll help visualize what do you need to include to actually free this and make your free body diagram. And let's come down below and we can sketch this in. So I'll get my general outline drawn. Should look kind of like this. I know at the top left corner at A, there's a pin right here. When I cut a pin, I should have pin reactions, an X and a Y component, what we're always going to put in for a pin. So I can say right here, I have an AX, and I'm just guessing a direction on this. And in the Y direction, I'll guess it goes up, AY. It's just an arbitrary choice in here. If it turns out I guessed wrong, the math will work out, they'll get a negative. I'm still going to report my final answer as a positive and give the correct correct direction on it. So we'll get those two in here. I know in the top right corner, there's this 500-pound force. So let's go ahead and stick that in there. It's going to the left 500 pounds. In my inside corner right here, there's a 1,000-pound-inch couple moment, so I can stick that on here. It's going clockwise in our given picture, so just draw that in, 1,000 pound inches. 1,000 pound inches. Let's get dimensions on. We'll get this rocker in here last. But I know from A to my inset corner is 6 inches. From that inset corner to the right edge is 5 inches. Does that location right here, does that matter for us? Our couple moment should cause the same rotation no matter what point I'm taking a look at. So it doesn't matter that it's right here. This would be the same as if I showed it here, over here. If we're looking for our support reactions, we could put this anywhere on here. Who cares that it's 6 inches in at this point? So let's ignore that for now. We're just going to say our entire width along the top is 6 plus 5, 11 inches. So 11 inches. And we can do that same idea going down from A, dropping down to the bottom. Again, it doesn't really matter where that couple moment's at. It doesn't matter that this is 3 inches and then 3 inches more. I could put this entire distance in here as 6 inches. We're getting the exact same info conveyed out for this. The very last thing that I need is my rocker at point B. I should have one force perpendicular to the surface it sits on. So if my arm is that surface, perpendicular to that, we'll be going up and to the left in here. Up and to the left. And the easiest way to figure out its angle is just to say, well, I originally had a 30-degree angle from horizontal. When I go perpendicular to that, I can just say it's the same angle, 30 degrees. I'll just measure it from vertical. So change the axis that you're measuring from. It's really all that we did here. 30 degrees still, though. Once I have that, I can come in and say my next step is just to start applying equilibrium into this. I can sum forces and moments. Let's name this force. Let's call that, it's not in the X or the Y direction, it's in both. So let's call that FB, the force at point B. And from there, I can come in and start trying to apply equilibrium. So in the X direction, I have AX and FB. In the Y direction, I have AY and FB, two unknowns in each of those directions. I can't really use one equation, one unknown there. So ideally, there's a point where I could sum moments about. If not, we have to make a system of equations. But in this one, I could sum moments right here at point A. I'd eliminate AX and AY. FB would be my only unknown. If I can find FB, then I could sum force in the X and the Y. With FB being known, I'd only have one unknown in each of those equations. So let's do moments here at A to start out our problem. So we'll come in and say with positive, going counterclockwise, let's sum up our moments about point A, this top left corner. If I'm doing that, AX, AY pass through there. We don't need to include them. But my 500-pound force, it's also going to pass straight through A. It won't cause moment either. So I need to get moment from the X and Y component down here of FB and moment from my 1,000-pound-inch moment. Is all I need to include in there. So let's deal with FB first. So this is equal to, let's deal with the Y component. If it's acting up here, that would cause a counterclockwise rotation about A. So put that in as positive. Because my angle comes from vertical, I need to say, when my angle symbol touches Y, I use cosine there. So 11, my perpendicular distance from A to that force, 11 cosine, or let's do it this way, 11 times FB cosine 30. 11 FB cosine 30. 11 is my distance, FB cosine 30 is that Y component. Then let's check our X component. Going to the left down below A would cause a clockwise rotation about A, so I need to subtract this off. Minus, my distance in here is 6 to get from A down to the X component, so minus 6 FB sine 30. Then the only other thing that would cause rotation is my couple moment in here. I'm going to go to the next line so I don't run into other things on the screen. But it's just clockwise. The location doesn't matter. I don't need a distance on that. I just put in plus or minus 1,000. It's clockwise, so I subtract it. Minus 1,000 is going to get us to 0. Equals 0. FB is my only unknown in here. Even though it shows up twice, it's the same unknown. So that would be one of my answers in here. I can solve this equation, and I'm going to get to that force at point B is equal to 153.22 pounds going up and to the left, perpendicular to the surface that it's sitting on. Once I know FB, well, now if I sum forces in the X, I'll have AX, this 500 pounds, and a known FB. AX is my only unknown. So let's go there. Summing forces in the X direction. Summing forces in the X. I have AX, I assumed it went to the right, so I'll put it as positive. 500 goes to the left, minus 500. FB's X component goes to the left. So I'll subtract this off. Minus FB, 153.22. And to get the X component, I just need to use sine. So sine 30 gets us to 0. AX is my only unknown in that. I can solve here for AX, and I'll get my second answer out. AX is 126.61 pounds. I get a positive number for AX when I solve this equation. That means in my free body diagram, I guessed the correct direction. It is going to the right. So we get magnitude and direction in our answer statement for our support reactions. That'd be my second answer. Finally, I have AY as my only unknown left. There are multiple ways I could solve this. I could come in and sum forces in the Y. I could sum moments at any point I want to take a look at other than something that AY passes through. But probably the easiest approach here is just to sum forces in the Y. And in general, as engineers, we want to try to tackle the easy approach. We're less likely to make mistakes if we do the easiest thing possible for our solution. If we make less mistakes, less stuff goes wrong, we're better all around. It's also easier for someone to follow our work if we've done the easy thing. So take the easy approach. Sum forces in the Y here. But I would have AY going straight up. AX and 500 are only in the X direction, so we leave those off. I just need that Y component of FB. So plus, because it points up, FB 153.22, 0.22 times, I just want the y component, so I'm taking the cosine. Cosine of my angle is 30 degrees equals 0. So solving that out, we actually get a negative answer out from this. We would solve this and get the AY is a negative 132.7 pounds. Remember though, when we do these, we always want to give our answer as a positive, not a negative, and then give the correct direction. So right now what I'm really saying is I have a negative force when I assume that it went upwards. Negative up, well, that's the same thing as dropping that negative and saying that's a positive and changing the direction. Positive going straight down. Negative up equals positive down. Change the sign, change the direction. We're really saying the same thing. So let's drop the negative and get the correct direction in here. That was negative going up. That'd be the same thing though as saying AY is a positive 132.7 pounds going straight down. The one other thing I would encourage you to do, because this will become more useful when we get to like frames, machines, down the road, is if we realize we got the wrong direction assumed, let's come back to our free body diagram. We're not going to change that arrow because that upward arrow ties in exactly to our equilibrium equation. We're going to come in and do something to acknowledge, I guess, the wrong direction here. I just put in a dashed arrow, so I'm going to show that going downwards in here. That way, if I look back on my work, or if I need to use this moving forward, I can say, hey, originally I guessed that it went up. That's what my work set up to do in here. That dash arrow tells me I know which way that really went. It's really going down. If I needed to use that down the road, which we will do later, I'd use it with the correct direction. I'd use it pointing downwards for everything when I try to use it again down the road. But again, 2D rigid body equilibrium is going to just show up over and over and over for us. We got to get these ones down. You can do it though. This becomes really second nature to a lot of engineering students. But we got to fight through it at the beginning. But we'll get you there. Hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Stick around. Let's get you an A with JJ.